Here's questions 5 through 8. So we've got Marilyn. She's lifting up on her suitcase 25.5 kilograms as shown. The suitcase is at rest, so even though she's lifting that up, it doesn't actually move. So we're going to draw the suitcase's force diagram. I don't need to use that box, so whatever. Okay, so we're going to start with, we're going to start with the box's force of gravity, the suitcase's force of gravity. So we're going to do 25.5 times 10 is 255 newtons. Then we're going to draw these forces in there. I'm just going to draw the horizontal and vertical. So I've got F Marilyn to the X direction is going to be 200. And F Marilyn in the Y direction is 150. Okay. Those are the only ones they gave us. We know normal force exists because the suitcase remains at rest and it's still on the ground. And then we know there's got to be something else to the right or to the left that balances out force of Marilyn. So we've got to have normal force up here. And because we want this pointing down to balance out these pointing up, we need something that can add to 155 that will equal 255. So normal force here is only 105 newtons because 105 plus 150 is equal to 255. Pointing to the left, we need something that equals 200, and that's going to be friction. That's 200 newtons. So anytime there's something pulling in one direction and it's not moving, that's because the force of friction is still bigger than the force of the pull, or equal to the force of the pull right now. And that's why she can't move it to the right and she can't lift it because she's not lifting it with enough force to overcome the force of gravity. If she lifted it with 255 newtons going in the, or over 255, she lifted with 260 pulling up, then she'd be able to lift it off the ground. And that's why she can't. No offense, Marilyn, I'm sure you could. Okay, station 6. We've got our scale on the ceiling. Why not? We throw this thing into the air, 1 kilograms, and it causes this, it strikes the scale, causing it to read 40. So there's no, this means no F drag. That's what negligible means. You don't have to consider it. So we're going to move free body diagram, moving upwards before hitting the scale. So this. Doesn't matter if it's moving upwards. It only matters if it's moving upwards if we have drag, which we don't. So the only thing acting on this is going to be Fg, which is going to be 1 times 10 or 10 newtons. And we are done. There is no force pointing up. There was at one point, someone probably threw, well, it says thrown, but this is after they threw it. So it's done. The force is done acting on the ball. Now it's just gravity, so it's going to end up slowing down. Or in this case, it's going to end up hitting the ceiling and applying a 40 Newton force to the ceiling, which means then that the scale will apply a 40 Newton force back down, and that's what we're going to call normal force. So we've got Fg equals 10 for the free body diagram when it's touching the scale, and then we've also got 40, that's normal force, and it's going to be pointing down because it's going to make this ball go down. It's not going to make it go up. So we've got 40 newtons pointing down and 10 newtons pointing down. So what is the net force on the ball when it strikes the scale? It's the 40 plus 10, so it's going to actually be negative 50 because we're pointing down. So I'm going to put in parentheses negative 40 plus negative 10. Okay. Number 7, we got Victor. He's pushing this box, 45 kilograms, so Fg is going to be 450. Across the ground is shown, so we can tell by the way he's pushing it that this thing is moving that way. We're going to draw the free body diagrams, and this one you don't always know forces, so it says if you don't know the value of the force, use the length of an arrow to indicate whether it's equal, greater than, or less than. Ooh, don't use that apostrophe. That's not the right apostrophe. So here we go. Victor's pushing the box at a constant speed on a floor with friction. So I can write down that Fg is 450. I can write that Fn, because it's on the ground, is also 450. I know that there's a force of friction pointing this way. And since it's a constant speed, I know the force of Victor is equal. So that should be about as big as that, okay? So those are equal. And that's my free body diagram. So because it's a constant speed, the net force is 0. And we know the net force is 0 because these forces balance out vertically and horizontally. Okay. Victor is pushing the box at a decreasing speed on a floor with friction. So FG is 450 again. It's not going to change our vertical motion, or there is no vertical motion, so it's not going to change our vertical forces. And it just says it's decreasing on a floor with friction, which just means that the force of Victor is less than the force of friction. So as long as you have force of Victor as a smaller arrow than the force of friction, then you're good. Because the direction of the motion is to the right, if it's slowing down, F net has to be pointing to the left, which means the left has to be bigger than the right. Next. Okay. Victor is pushing the box at an increasing speed on a floor with friction. And I keep saying a floor with friction so you guys know to put F friction in there. So now we know if the speed is increasing, that means F net points in the same direction as D. So I'm going to make a big F Victor and a small F friction. Okay, so this guy is much smaller than Victor's force, which means he's overcoming the force of friction and he's increasing the speed. All right, last one. The last one I gave you guys is that Victor's pushing the box at an increasing speed along a frictionless floor. So none of this at all has to do with vertical motion, which is why these Fn and F gravity keep being the same. We didn't change the mass either. There's no friction, so there's nothing pointing to the left. So it doesn't matter what size I put for Victor's force of the push because there's nothing pointing to the left. So no matter what force he pushes with, the box will move. Okay. Last one. We've got 3 force diagrams, and we're going to match these to the different descriptions of motion. So we have an object moving at a constant speed to the left. Constant speed means F net is 0. And the only one where F net is 0 is this, B, because the left and the right arrows are the same length. Okay. An object at rest remaining at rest. F net equals 0. So again, that's B. An object moving to the right and getting slower means that F net has to be pointing to the left. So that means the left arrow is bigger than the right arrow. So here's left arrow, here's right arrow for C, so that's got to be C. And then the last one says an object moving to the left and getting faster. You can't really see it down there, my bad. But moving to the left and getting faster means, whoops, that was C. Moving to the left and getting faster would mean that we would have D going that way and F net would be pointing in the same direction. And we know that the one that has F net pointing to the left is C. See? So that would be C. These are all the explanations you really need, honestly. Okay, so if something moves to the left and gets faster, we know F net will be pointing with it. If it moves to the right and it gets slower, F net's pointing against it. If we were, so maybe you thought, well, what about A? Maybe you were bothered by the fact that we never used A. We could say this is something that is moving to the right and getting faster. Or if it was moving left, it would get slower. That would be for A. But we didn't use that. I didn't give you that.